Alright guys, welcome to our Princeton Review help video. This first one is meant to help you guys out with page 221. Page 221, numbers 3 and 4. Now I'm going to let you guys do number 3. It's easier because we've done one like that in our notes. So if you guys want to go back to, I believe it would be unit 4 where we did these kinds of problems. I think it would be like 4.9 or 10, one of those two lessons. But we definitely have one like number 3 in our notes already. So I'll let you guys check that out. But this one's a little bit different. We didn't do one like this in our notes, but the same steps will apply. These are related rate questions. The reason I know that is because they're telling me the rate of one thing, and then they're asking me the rate of another. So that's a related rate question. So the first step when you're doing a related rate question is to draw a picture of what they're talking about. So it says the sides of an equilateral triangle are increasing. So we're talking about an equilateral triangle. That's a triangle that looks like this, and it has a side length of S, and on an equilateral triangle all the sides are the same length. Okay, and that's pretty much all we would need to draw for that. They tell us that the sides are increasing at a rate of 27 inches per second, and then they want to know how fast is the area increasing at the point in time when the sides are 18 inches long. All right, so we're done with our picture there. Let's move on to step 2. Step 2 is to identify the given rate and label it appropriately. So the sides of an equilateral triangle are increasing at a rate of 27 inches per second. And that is going to, we always write it like this, d over dt. The only thing that's ever going to change is the variable you put here, and that represents the rate of what? What's changing? In this case, we're talking about the sides. Now, it's important to pay attention to whether it says increasing or decreasing. In this case, it says that the sides are increasing, so my 27 inches per second is a positive number. But if they ever say that it's decreasing, or if the problem would suggest that it's decreasing in some way, then you would put a negative. But in this case, it's going to be positive. The third step is to identify the desired rate, or the rate that we're trying to find. What rate are we trying to find? They're asking us how fast is the area increasing. So dA dt. All right, so now this is where we, I think on the AP exam, I think they would tell you the formula. They don't expect you to remember all the different geometry formulas that exist. But there is a formula, and that's what step 4 is all about. The formula, we're looking for a formula that will connect our two variables that we care about. I care about the sides because I know that rate. And I also care about the area because that's the rate I'm trying to find. So I'm looking for a formula that will tell me what's the area of this triangle based on its side lengths. And there is a formula for the area of an equilateral triangle. And if you guys ever don't know, just Google it. I think I know what it is, but I'm actually going to pause my video right now and Google it just to make sure because I don't remember the formula that well. All right, so when I looked it up, I found the formula for the area of an equilateral triangle is given by A equals the square root of 3 over 4 times the side length squared. So once again, I'm pretty sure on the AP exam they would tell you the formula. Hopefully they wouldn't just expect you to memorize that kind of stuff because, I mean, why would anybody have that memorized? I don't know. But anyway, number 5. The next thing we want to do is we want to find the derivative of that formula with respect to t. So I'll put differentiate the formula. Okay, and so I want to find the derivative of that formula with respect to t. So taking the derivative of a, I end up with dA dt. This is a constant multiple, so it's just going to stay there. Constant multiples don't change. The derivative of s squared, well, the derivative of s squared is going to be 2s, right? But don't forget that when you're doing derivatives with these types of problems, when this variable down here doesn't match this variable here, we're going to treat that like an implicit differentiation. So after you find the derivative like normal, you're going to multiply it by the s prime, or in this case we'll call it ds dt. Okay, now we could simplify this formula a little bit. I can multiply the 2 here by this 3/4, and I would end up with 2 radical 3 over 4, and then the 2 over 4 can reduce. So if I were to multiply those together and simplify, we can write this out a little bit simpler so it looks more like this. If you multiply those together. All right, step 6 is to start plugging stuff in. So we don't know what dA dt is. That's the whole point of the problem, actually, is we're trying to find that rate. So we're going to leave that as dA dt. Radical 3 over 2 is just a constant, so it stays there. But s we know, and the problem, they're asking us to find dA dt when s equals 18. So we're going to plug in 18 for s. And ds dt we also know. They told us that in the problem as well. It's 27 seconds or inches per second. All right, and then we're going to go ahead and just multiply this whole thing together, and we'll be good to go. So you could think of these as being over 1, right? I would divide the 2 into the 18 to get 9. And then I would do 9 times 27. And I end up with 243, and then that square root just stays there. We don't want to forget our units, by the way. Now, since my triangle is being measured in inches and the time is being measured in seconds, area is going to be square inches, and time is still seconds. So area, square inches, time, seconds. And so the answer is 243 multiplied by the square root of 3 square inches per second. All right, and so as for number 3, I'm going to let you guys do that. Check out your notes if you need help. It would be like in 4.9, 4.10 or something like that. There's some great examples in there that will help you out with that one. Let's move on to the next one. Okay, let's go ahead and take a look at this next page here, which is page... All right, and so the next page we're going to be working on here is on page 226. I'm going to do number 3, and then I'm going to let you guys handle the next question on your sheet. It's not added. Your next question actually is not even in the book at all. I made it up because I wanted you guys to practice the problem that's like this one, but they didn't have any more in the book like this one. So, and it's actually a pretty common AP question, so I thought it was important. I'm going to do this one. This one's a little bit harder than the one that I gave you guys to do, so you guys will get the easier one, and I'll walk you guys through the harder one. But the only reason it's harder is because of the derivatives and the solving and stuff. But it's really not harder in the basic steps of the matter. Okay, so they give us a position function. A position function tells us where a object is located at any point in time. So on the time interval from 0 to 4 pi, if you were to plug in some time value in between there, like let's say you plugged in 2 pi, or in other words 6.28. Well, if you plug it in and get an answer, the answer will tell you what the object's position is at that point in time. Okay, so just imagine like there's a dot traveling on an x-axis, right? And well, if I were to plug in 6.28 and solve it, I would end up with 0. So the object would be located at position 0 on the number line. Okay, so that's what a position function does. It just tells you where something's located. But this question is asking us, find the times when it changes direction. Now, direction can be found by looking at velocity. Okay, a negative velocity means you're moving left, And a positive velocity means that you're moving to the right. A zero velocity is where you start changing your direction. So the point in time when the velocity equals 0, that's an indicator that the object is changing positions, right? Because if an object is moving to the left and it stops all of a sudden, and then it starts moving to the right, well, in order to go to the right, it had to stop. And when it stops, there's no movement. There's no direction. And so that would be 0. So we're looking, so this question here says, find the times when it changes direction. Well, we need to look at two things. First of all, we want to find where is the velocity equal to 0. And then second of all, we want to make sure that it is actually changing direction at that point. Okay? It is possible for an object to be going, to stop, and then to keep going, right? So we want to make sure that it actually does change direction. It's not just stopping. So what we're going to do then is we're going to, first of all, find the velocity. Now, as you guys may recall from chapter 4, if you have a position function, the velocity function can be found by just taking the derivative of your position function. Okay? So step 1 is going to be to find the derivative. Step 2 is going to be to set it equal to 0 and solve. And after that, we're going to do a number line test. Those number line tests come in pretty handy, don't they? We've used them for a lot of different things. We've used them for talking about absolute values. We're using them now for position particles. We're also using them currently in our new unit right now when we're talking about points of inflection and relative extrema. Really useful stuff. So those number line tests are very helpful. So make sure you know those. All right, so there's our steps. Let's go ahead and begin here. So step 1 is to find that velocity. So let's do that first. So the derivative. The derivative of this is going to be a chain rule. First of all, you do the derivative of the outside function, which is sine. So the derivative of sine is cosine. And then you multiply that by the derivative of the inside, t over 2. Now remember, t over 2, that's the same thing as 1/2 t. And so when you take the derivative of this, you just take the number off the front. So it's the derivative of the inside is 1/2. So there's my derivative. Step 1's done. Move on to step 2. We're going to set it equal to 0 and solve now. Well, first thing we might do is get rid of this half by multiplying both sides by 2. So if I were to multiply this side by 2 and this side by 2, we still have 0 on the left, and now this is canceled on the right. The next thing that we're going to want to do is we're going to want to find when does cosine equal 0 on the unit circle. Cosine equals 0 on the unit circle in two places, up here and down here. The one on the top is pi over 2, and the one on the bottom is 3 pi over 2. Okay? So, if this angle in here is pi over 2, then cosine of that will equal 0. If that angle on the inside is 3 pi over 2, then that would also make 0. So that means that t over 2, the inside, is either equal to pi over 2 or it's equal to 3 pi over 2. And if you just multiply both sides by 2, you're going to end up with two answers for t, which is, if I multiply this side by 2, we end up with t equals pi. So that's one place where the derivative equals 0. In other words, the velocity is 0. In other words, the object has stopped moving. And so the object has stopped moving at the point in time when t equals pi. Another time when the object has stopped moving, if I solve for t, is at 3 pi. So those are 2 points in time where the object has stopped moving. And remember, we want to look for answers on this interval between 0 and 4 pi, and both of these are between 0 and 4 pi, so we're going to keep both of those answers. Now remember, just because the object stops, that doesn't necessarily mean that it's changing directions, right? And that's why we're going to go ahead and do our number line test now to make sure that it actually changes direction. All right, so here we go. Number line. Let's go ahead and put our 2 points in time at which the object stops moving on here. And it starts at 0 and ends at 4 pi according to the problem. So I have 3 intervals I want to look at. Okay, so I want to see what is x prime of t on this interval. I want to see what's x prime of t on this interval. And I want to see what's x prime of t on this interval. Because remember, if the derivative, which is the velocity, is negative on that interval, that means it's moving to the left. And if the derivative, which once again represents the velocity, is positive, that means the object's moving to the right. So let's pick a number between 0 and pi. And I think a really good one to pick would be pi over 2. Now let's pick a number between pi and 3 pi. Well, how about 2 pi? And then finally, let's pick a number between 3 pi and 4 pi. How about, gosh, what's a number between those 2 things? All right, well, there's a slightly easier way, which involves a calculator. Then there's a little bit more of a complicated way if you don't have a calculator. Now, the easy way would be just to change these into decimals and then pick a number between those 2 decimal values and plug that number in on your function on a calculator. But not all questions are like that. So in this case, I'm going to show you the harder way just in case you ever come across a problem where you don't have a calculator. So what can we do? Well, 3 pi, if I add a little bit more to it, then I want to add just enough to where I don't get 4 pi, but just a little bit more. So what I'm going to add is I'm going to add like half a pi. Because if I add a full pi, that's just going to get me all the way over to 4 pi. But I'm going to add a half a pi. That way, we'll actually get a number that's between those 2 numbers. So we need to get a common denominator. And so the answer here would be 7 pi over 2. So 7 pi over 2 would be a good number to plug in here. All right. So let's continue. So now at this point, we got to actually plug these numbers in to our little formula here for the derivative. So my derivative, in case you guys don't remember, let me put it back up there. Well, hopefully you remember. Hopefully you guys are writing this down with me. But anyway, the derivative was cosine of t over 2 times a half. That was my derivative. So let's start by plugging in pi over 2. All right, so if we simplify pi over 2, it becomes pi over 4. And cosine of pi over 4 is radical 2 over 2. So let me make a little more writing space for myself here. Times a half. And honestly, we don't really care too much about the final answer, although the final answer would be radical 2 over 4. We care more about the sign, and that's a positive number. And since that's a positive, that means my object is moving to the right. So since my velocity is positive, my object is moving to the right on this interval. And we're just going to continue doing that for the other 2 points. Let me do another one. The next one will be a little bit easier to plug in, I think. It's not a fraction. All right, so we have x prime of 2 pi, and we're plugging that into our derivative. Now 2 pi over 2 simplifies into just pi. Cosine of pi is -1. And -1 times a half is -half. And once again, the number doesn't matter, but the fact is that it's a negative number. That's what matters, is the sign, and that means we're moving to the left. Okay. Last one that we'll check out there. Let's go ahead and do the other one. The last one is we want to plug in 7 pi over 2. So 7 pi over 2 divided by 2 becomes 7 pi over 4. 7 pi over 4 is right on our unit circle. It's radical 2 over 2. And so we actually get the same answer as the first one. It's positive once again, and therefore we're moving to the right. So from this, you guys can see that between 0 and pi, oops, my bad. Between 0 and pi, the object is moving to the right, and then it stops all of a sudden at pi, and then it starts moving to the left on the interval from pi to 3 pi. And then it stops once it gets to 3 pi, and then it starts moving to the right between the last two numbers, 3 pi and 4 pi. Okay, so now the trigonometry here was probably a little bit distracting to you guys. I don't want you guys to get distracted by the trigonometry. I want you guys to focus on the process, okay? So the process was a 3-step process, okay? Step 1 was to find your derivative. Step 2, set it equal to 0 and solve. Step 3, number line test. Now the one that you guys are going to do is going to be much simpler, okay? Because I just want you guys to get used to the process. You're doing number C, or letter C there. It says if the position function is so on and so forth. I give you a polynomial. Polynomials are nice. All right, let's go ahead and move on to our next one, part D, page 310, numbers 6 and 7. Right, so here's page 310. And we're going to do number 6 and 7. I'm going to go ahead and do number 6. I'm going to let you guys do 7 after that. All right, so we're integrating. All right, now, back in Unit 2, I gave you guys a little worksheet on, at the very end of the unit, about how to decide what integration strategy to use. And in this case, you would probably want to do some U substitution. Now, I tried this problem once myself, and I was doing it wrong at first, because I thought maybe this whole thing right here was the U, but it didn't work, because the whole point of U substitution is it's supposed to cancel everything out and leave you with a nice, clean, simple-looking thing to integrate. And then I got to thinking, okay, I need to find something else. So a lot of times when you're looking for the U, it's just a guess and check process. And in this case, I've discovered that U, in this case, the best option would be the ln of x. Now, how would I know that? Well, a lot of times you just look at the inside function and that's your U. But actually, there's two inside functions here. This, another way of writing that is like this. And so technically, ln of x is also an inside function. So there were really two options for which one was going to be the inside function. And the first one I chose didn't work, and so I went with the second one, and voila, it works. All right, so there's my U. We're going to find the derivative of U, because that's what this function is equal to, with respect to x, because that's what's inside of it. So we're doing du dx, and the derivative of ln of x is 1 over x. Now we want to get dx by itself, so I'm going to multiply both sides by dx. And I still don't have dx by itself, though, so now I want to multiply both sides by x. And now we've got dx by itself. All right, and so here's how u substitution works. We're going to replace the dx with x du, and we're going to replace the ln of x with u. So if I do all those replacements, here is what it would look like. This integral would become x du, because we're replacing dx with what it equals, and dx was equal to x du. This little x down here in the bottom is going to stay for now. Then we had 1 plus ln of x being raised to the second power. But we're going to replace the ln of x with a u, so now it's u being raised to the second power. At this point, these cross off, and I'm left with this expression. And I like to put the du off to the side. I don't like it on the top like that. That's a personal preference. Now, there's a formula for that. I haven't seen it in a while, but you guys might recall that that is the integral of that is an arctangent. And don't forget your plus c. When you do an arctangent, you always do 1 over your a, which we haven't figured out yet, and then you do the square root of that number over your a. So now instead of u squared, it's just u because we took the square root of it. So what's the a? The a is the square root of this number, which is 1. So a simpler way to write this would just be like this, right? Now, if this is all looking really foreign to you, in all the extra time that I'm sure you guys have, because I know you AP kids, you got nothing to do, right? But that's a joke. But if you have extra time, remember those flashcards I gave you? I give you a lot of flashcards, but I would probably spend a long time with integral flashcards alone, just because you don't see them very often. That just seems to be an issue. Derivatives, students got those pretty well usually, but integrals, for some reason, they just don't stick as well. So good. Make sure you review those every once in a while. But anyway, here we go. We have arctangent of u, and our u was ln of x, right? Plus c, and now we're all done. So there it is. Now you're going to do a similar thing here on number 7, okay? You're going to do a u substitution, and your u is going to look very similar to where my u was at. You're going to, after you finish your u substitution and you clean it up, you should end up with some kind of an arc function. It's either going to be arcsine, or cosine, or cosine. I'll let you guys see if you can figure it out, but there it is. So go ahead and see if you guys can figure out number 7. Let's move on to the next set. All right, more integration practice. Here we go. So what do you think your u is going to be for number 5? Because there's no integration rule that works for number 5 the way it looks right now. So if there's no integration rule for the way that it looks, then we have to mess with it somehow. And a lot of times the solution is to do u substitution. So what do you guys think the u might be? Well, I only see really one option for that, and it's whatever's inside the parentheses. It's not like the other one that had double parentheses, so to speak. This one really only has one option, and it's this. So let's try that out and pray that it works. Here we go. The derivative of 1 is 0, so that just goes away. The 2 is going to stay because it's a constant multiple. And the derivative of a square root, there's a nice little shortcut. It's always going to be 1 over 2, and then that square root. And then if necessary, multiply it by the derivative of the inside of the square root. But in this case, the derivative of the inside would just be 1, so it's not going to do anything. And then these cancel. So now I have this. Nice. By the way, a good way to identify your u, if you're good enough at doing this kind of stuff in your head with enough practice, which many of you probably aren't, because you're still getting used to this, and it's been a while since we've seen integrals. But if you do get good practice, you pick a u in your head, and you ask yourself, if I take the derivative, what would I get there? And if you can get that in your mind, do you see that somewhere in the problem? I do. It's right there. If you see the derivative in the problem, that's probably the correct u that you picked. So 2 things. The u is usually an inside function. Second of all, when you take the derivative of it, that derivative should be floating around in that problem somewhere. But anyway. Now we get dx by itself using the same process as the last page. So in this case, it would come out to be square root of x du equals dx. All right, so now in the original problem now, I'm going to replace the 1 plus 2 radical x with u, and I'm going to replace the dx with x du. And let's see what that comes out looking like. The whole point of u substitution is to rewrite the problem in a way that is less complicated looking. All right, the irony is it's a rather complicated process to make it look less complicated, but I guess that's how it is. All right, so we have that, and that's what it would look like if you did that. So I like to get rid of those. I also don't like having the du on the top. I like to put it down on the side, and so we have this. And what do you know? Now that I've done all that, it's a classic LN problem, if you remember your integrals. All right, and then the u is, we said 1 plus 2 square root x. There we go. And that's the end of that problem. So I'm going to let you guys handle number 6. I'm tempted to just tell you what the u is. It's not that tricky, honestly. But you have two options, okay? I'll tell you that. It's either going to be this or it's going to be the whole denominator. See if you can figure it out. I'm going to let you guys pick which one is the u and see if you get it. All right, I'm going to move on to the next one here. We just finished page 318. We're going to move on to page 371 now. All righty. So now we are on page 371. And we're going to do number 2. All right, it's been a while since we've done one of these things here. So if secant x dy dx equals 4 tangent y, and y equals this, find an equation for y in terms of x, okay? Now, these are really important questions. You will see it on your AP exam, and they're worth a ton of points. These are the ones that I emphasized way back in lesson, or unit 2. Just, man, make sure you know how to do these kind. It's been a while since we've done one, so you might be rusty, but the steps hopefully shouldn't look too foreign to you. So the first step is to separate the variables. In other words, you want all the y's on one side and you want all the x's on another. So I'm going to take this expression here, secant x dy dx equals 4 tangent y. And what I want is I want to get this whole thing here. I want to get this tangent y to be on the other side with the dy. And I want to get this dx, a different color here. I'm going to take this dx and this secant x, and I want to get those over here. I want to get them to the other side. That way all the x's are on one side and the tangent is on another. So now, first of all, what I would do is I would divide both sides by tangent y. You can do it one step at a time. So, uh-oh. Whoops. It happens. All right. So I'm going to move the tangent to the other side by dividing tangent y to the other side. All right. Cool, so I got the y's on one side of the equation. Now I want to get the x's on the other side. So the next thing I would do is I'd multiply both sides by dx. You can't have the dx or the dy in the denominator. They have to be in the numerators for these types of problems. So we have that now. So that leaves me with secant x over tangent y. And that leaves me just dy now equals 4 dx. Finally, now we're gonna divide both sides by secant x. That way these cancel out here, and I'm left with 1 over tangent y dy is equal to 4 over secant x dx. Now I would encourage you guys, after every step on these, to try to, after you hear me tell you what to do, you just try it, because I don't have another one for you to practice in here, so this is your opportunity to practice. But the next step is probably something that you wouldn't think of, because it's not something we do very often. But if you did, you're awesome. That's amazing. The second step is going to be to integrate both sides. But before I get there, this step is not exactly the one I was talking about. The integration, you guys might be able to pause the video and do that on your own. This next step that I'm about ready to do before that, though, may not be obvious to you. I'm just looking at this, and I know that we have no way to integrate these problems here. We never learned anything like that. But I also know my trigonometry. And I remember from trigonometry that 1 over tangent is the same thing as cotangent. And we do have an integration rule for cotangent. Kind of. And then for secant, well, secant is the reciprocal of cosine. So if you take the reciprocal of that, this just becomes cosine. And we do have an integration rule for that. And then finally, something that's going to help us out along the way is we're going to rewrite this as, I'm running out of space here. Let me make some space. Cotangent, you guys may recall, is cosine over sine. All right, so now that we've got this, I had to do a little bit of trig there. Oh, that's supposed to have an x next to it. I had to do a little bit of trig there. That was a little bit, it's like one of those things where it's like, as a math teacher, I'm like, oh man, I wish they didn't have to stress out about these tiny little weird details that you never see. But what I do want you guys to make sure you know how to do is these steps here. All right, so I got you past the nasty part. Now you guys should be able to integrate both sides. Now, I would encourage you once again to be doing this, not just watch me, but for the left side, when we integrate the left side, make that a u, and then I'll let you guys do the rest. For this one, integrate that side, you don't need to do anything special. There's a nice, simple integral rule for cosine already. So, go ahead and pause the video here and see if you guys can get the solution, and when you unpause it, I'll show you what I got. So that's what I get down at the very bottom. So when you do your u substitution at first, it would look like this. If you let u equal sine y, you would end up with cosine y over u multiplied by du over cosine y. Then the cosine y's cancel and you're left with just a nice simple natural log. And the natural log of would be ln of u. In this case, the u is sine y, so there's that left side. On the right side, the constant multiple stays, and the integral of cosine is simply sine. And we don't want to forget our plus c. So there's the end of step 2. So step 1, separate the variables. Step 2, integrate both sides. All right, now let's move on to step 3. Step 3 is going to be to find c. And the way you do that is by plugging in your initial condition. So I'm going to plug 0 in for x, and I'm going to plug pi over 6 in for y into this formula down here. Okay, so let's see what that looks like. Okay. Now sine of 0 is 0, and 0 times 4 is 0, so this whole thing just goes away, and you're left with c equals this. It's kind of nice. Didn't have to do much work there. We could actually probably simplify this a little bit, though. Sine of pi over 6. What is that? Sine of pi over 6 is a half, actually. Nice. So there's my c. So I'm going to go ahead and replace my c in my general solution, is what that answer was called. I'm going to replace my c with what I just got. And now it's called a particular solution. Ringing a bell? Hopefully. It's been a while. All right. Now the last step, if you don't ever, if you find that step 4 is hard, because step 4 sometimes can be a lot of work. But if you can get to this last step, awesome. You've got most of your points anyway. But if you can actually finish step 4, awesome. The last step is to get y by itself. So solve for y. But in this case, I'm looking at my choices, and I don't even see that as being necessary. But I don't see anything that looks like my answer. You guys see anything on here that looks maybe close to my answer? I don't. So that means that even though maybe my answer's right, maybe there's a little bit more math I need to do to get it there. So let's just start trying to get y by itself, and we'll see what happens. In other words, I'm looking here, I can already tell there's a sine y, right? Since there's a sine y right there, I know it's got to be one of these two. We don't have to worry about those. So really all I need to do is get rid of that ln. And if I can get rid of that ln, hopefully this right side will match one of these, and we'll be good to go. So let's go ahead and do that. Now, how do you get rid of an ln? Do you guys remember how to do that? You get rid of an ln by raising both sides to the e power. So if you do e ln of sine y is equal to e to the power of 4 sine x plus ln of half. This cancels out. Okay, we're getting warmer. I got the sine y by itself. All right, now what's our guess? Let's look at our options here. Sine y. I see e4x. I see sine y. This one is a sine y and e4x and a half. There's a half. Okay, so at this point, if I was doing a test, I'd say, oh, well, that's probably it. I'm just going to pick that, right? But I'll actually show you guys how you can get that. We talked in this lesson, which has been a while ago, so I understand if you don't remember. But we talked a little while ago about how whenever you have an exponent where two pieces are being added together, like 4 sine x plus ln of half, you could rewrite that as a separate e. And since you can rewrite that as a separate e, now this e will cancel that, leaving you with a half. So this whole thing here just becomes a half now, and that's what goes in the front. Oops. And sure enough, that would be option D. Multiple choice is nice, huh? Okay. That problem wasn't nice, but multiple choice is nice. Okay, let's go ahead and let's take a look at our next set here. We're getting there. Almost there. One more page. Page 369. Let's back it up a little bit and see what that looks like. All right. Page 369, number 5, wasn't it? Number 5, yes. Okay, you know what? This one, I'm going to ask you guys to do it. It's much easier than the one I just did. It doesn't have all the weird little trigonometry tricks where you have to rewrite things in a different way. But if you just follow those steps, get all the variables on one side, the y's on one side, get the x's on the other, then you integrate, then you find c, then if you can, on this one, yeah, they do want you to get the y by itself. So follow the steps I gave you. This one's much easier than the last one I gave you. Just follow those steps that I wrote in black on the other side and you'll be good to go. Much easier than the one I did. Anyway, we'll stop there and I'll bid you guys good day and we'll see you next time.